Okay. Now, here we go. Sorry about that. Now, what we're gonna do is, so far, like I think we only have like 3 more things to worry about. And one of the things that we're gonna be doing today is designing the vertical bracing for the building. Okay. And this way you guys can see, basically what we're gonna be doing. And so wind loads on primary structure. Now, because it's the primary structure, okay, I think I've explained this once before, but I'll talk about it right now, is that when you have a building, okay, and you have the wind loads acting on the building, okay, when it comes to the primary structure, okay, you just worry about the external forces. The reason why you don't worry about the internal forces is because this one tends to cancel that one, and that one tends to cancel that one. So since these cancel each other, then when you add these together, and therefore you only have to worry about the forces acting, okay, on the exterior of your structure. So that's why we there's 2 different diagrams when you want to calculate the loads. And of course, the ones that we're going to be doing today is exactly the same ones that you guys did in structural analysis. So here we go. So we only have one equation. We only worry about the external wind loads, and of course the same equation applies. Okay, so in other words, the importance factor, the reference velocity, and so on. I'm going to go through this a little bit more quickly because we've done it so many times. And so the importance factor, the reference velocity, and the exposure factor, the gust factor, and okay. Now, of course, we know that in our case we have, like, I'd like to repeat this. So keep in mind that when it comes to wind, okay, look at the serviceability. The importance factor is what brings your loads down to much smaller when you're calculating serviceability, and that's why we use a smaller load. And no matter what the importance factor is, this is for strength and this is for serviceability. So that's the only thing I want to repeat so that people could understand why we only take 75% of whatever we have. Okay, so we take 75% of this, 75%, 75% of your, okay. Now, of course, here we've seen this before, it won't change. So therefore, for some reason, it's taking so long to go there, but we'll, what's happened? We've, for some reason, I've lost my, oh, guys, I apologize. I've lost my PowerPoint. I'm going to have to go back. I don't know why that happened. I don't know why that closed. I must have accidentally closed the okay, so here we go. Back to this. Let's hope that this is up and running. Yeah. Apologize for that. Share. Close. Okay, so slideshow. I hope. Okay, so I apologize. I accidentally closed the file. Okay, so here we go. This should work now. Yeah, there we go. So therefore, like whenever you want to get some climatic information, you know that for Montreal, no matter where you are in Montreal, the value of the 1 in 50 is 0.40 kPa, and that's what you're going to be using to calculate your load. And therefore, now, like I said, To be on the safe side, you always assume that you're going to be in an exposed area. If you want to be considered to be in a rough terrain, of course, you're allowed to reduce this to 0.7 as opposed to 0.9. Now, this is what we saw last year, okay? In structural analysis, this is the same figure here. And what this, and of course, what this figure gives us, okay? It gives us the value of CP and CG combined, okay? Now, depending on the angle of the roof, and of course, our angle is flat, so we're looking at here, okay? So it gives us the pressure at the midsection and at the edges or at the ends, okay? So 1E, 3, I'm not worried about, I'm sorry, I'm not worried about these values here because this is for the roof. And again, this is for, so therefore, I'm going to be looking at the wind pressure on the ends or the edge here, and the ones here. So these are the ones that I'm concerned about, right here and right here. Those are the only ones that I'll be concerned about in terms of doing the calculations for the forces I need to resist. And of course, you got the ones that are parallel to the ridge, okay? I'll be doing it only perpendicular to the ridge because I think that that's going to be the stronger one. Yeah, so. Now, here they're saying that the value of the CPG, okay, for low rise, okay? In other words, we are in that category where the height of the building is less than the shortest dimension in plan view. It is less than 1, and therefore, or we don't exceed, so therefore we're allowed using those values. The value, okay, interpolated linearly and so on, okay. Now, this is good to know. The reference height for pressures at mid height, Now, the thing is that this is what you want to know, like, how far do you go in order the end zone Y should be the greater of 6 meters or 2Z? Okay, I simply take 6 meters unless this 2Z is going to be, okay, where Z is a gable wall. And okay, so in other words, here we have, okay, the gable wall. So, so I like to take 6 meters as being the length of the end zone. I like to be conservative. Or what they also say, if you want to be conservative, like you can go up to where your first frame is. So in other words, if we have our spacing here of 5 meters, okay, you're allowed to go up to 5 meters where your first frame is, and so on and so on. But I believe I took 6 meters to be on the safe side. Z is a lesser of 10% of the least horizontal dimension, or 40% of the height, but not less than 4% of the least horizontal dimension, 1 meter. So this very rarely will this, like unless you have a very, very wide building. So 10% of this was 2.7 meters, which is no good. 40% of the height, which is 2.4 meters, and 60% of the least horizontal. So none of this works. So therefore, I will stick to the 6 meters for the end zone. And that's what I'm going to be using. So therefore, now, in our case, I believe that our first frame is at 10 meters. So I like to go all the way up to my first frame. Even though I've got a wind column here, I like to go all the way up to my first frame here as being my end zone for the 1E and 4E values, okay? And of course, we have here, the building is 50 meters high, so I'm going to go only to half. Why? Because if you look at your building, you're going to be having a vertical brace on this wall, you're going to have a vertical brace on that wall. So you can assume that this one's going to take care of half the building, this one's going to take half the building, and then in the other direction, you have a vertical brace there, a vertical brace. Whatever is good in the short direction will definitely be good. I'm sorry, whatever is good for the long direction will be good for the short direction. So we're just going to repeat it there. And that's why I take, okay? Now, here what happens is this, okay? When the wind is blowing, okay, all the wind here will go down to the foundations. So therefore, the structure will not have to transmit those loads to the vertical braces. So therefore, I don't have to worry about the winds on this part of the wall, okay? And then all the winds at mid-height going up will be going through the roof and will be transmitted to that vertical brace that you have there. So that's why I'm only going to be calculating the loads that are acting on the upper half of the wall, because everything on the lower half of the wall, in theory, should get transmitted right down to the foundation wall right away. And that's why. Now, this here is just so I can calculate my tributary area with respect to the edge or the end of the building, whatever you want to call it, E for edge or E for end, okay? And this is for the middle section here. So in other words, so therefore I apply the different CP, CG values to calculate the pressures on this surface and on that surface. So like I said, guys, whenever you're doing anything with regards to structures, first thing you have to establish is your geometry. Once you've established your geometry, then you worry about your loads. Without this, you can calculate all loads you want, you won't know what to do with them, okay? So therefore, first thing I worry about is what is the tributary area that this surface is going to have so that I can calculate the wind pressure here. And then what is the tributary area of this surface here? And of course, this would be 15 times 3, and this would be 10 times 3. So that's a tributary area. So therefore, I can convert the force here and the force here, and then add them together to get what the force is going to get transmitted into my vertical brace. That's why I'm doing this. Now, once I've done that, of course, I go and calculate my loads. I like, whenever I do wind loads, I like to put them like, I do this on an Excel spreadsheet, okay? Now, does anybody have a calculator? I haven't calculated these two values here for some reason. But does anybody have a calculator so we can do this here? So 1E, this was the importance factor. This was the value of CPCG. Of course, we're in exposed, therefore the CE value is 0.9. From the table, I get 0.15, and the pressure here is 0.4441. And for 4E, well, first of all, I want somebody to double check the math, make sure it's okay. I think I did this in Excel spreadsheet, but just double check this math here. Let me know if it's okay. Double check the math here, make sure, and give me the value that we have here and here. And in the meantime, I'll be enjoying
Sir, 1E minus 4E is equal to 0.1426.
1E minus 4E is equal to what?
0.126.
Okay, 0.12, impossible.
Thank you.
It's impossible that the sum of the two is less than just one of them. Are you doing the algebraic?
It's 0.702.
Yeah, I got 0.702.
Yeah,
Okay,
exactly.
thank you. You know, like guys, it's the algebraic difference, you understand? And the reason why they do this is because, like guys, you have to look at it this way, okay? Here the wind is pushing on, if this is your wind direction, here the wind is positive, here it's negative, but because they are both acting in the same direction, you don't subtract one, well, you do subtract one from the other, and that's gonna turn this one to be added to that one. That's what they call the algebraic difference. So what did you get here, guys?
702.
0.702. So that's KPA there, okay? Now here, there should be like 0.4 something. What is it? First of all, did you check to see if these numbers were good?
Yes.
They're
They are
okay? Those are okay, good. You know, because guys, we're supposed to be doing this together. I mean, you're supposed to be doing it. So what is it? What is the algebraic difference between this one and this one? You know,
0.468.
468. Okay, so guys, keep this in mind because I'm going to be asking you for these values. Okay, so write this down somewhere. I won't have them, and you guys are going to have to do the calculation. So therefore, in terms of the surfaces that we're looking at before on the previous page, so 0.072, you said? I'll write this down so I won't forget. 0.072, and the other one is 0.468. Okay, so if we're looking at this, if I go back, okay, so right here, that's the pressure acting here of 0.072, and then here we have a pressure of 0.468 acting on this surface. So if I want to know what the force that's going to be acting on the surface, I multiply by the tributary area. If I want to know the force acting on this surface, and in plan view, what's going to happen is, of course, now usually I don't get into this because it's, you know, like you can use the roof as a transmitting mechanism of the lateral forces to the vertical brace here. Okay, and therefore all you got to do, and there, this is a, if you go to Can-Am, they even show you how you can calculate this diaphragm to be able to transmit the load there. And therefore, all I really want to know is that when I look at my brace, how much of a force does my brace have to resist? And that's what I'm going to be calculating right now. So now the specified force times my tributary area. And and of course, the factor is 1.4. So you guys do this calculation, because like, in other words, take the value there times that tributary area, and somebody give me the value here. So in other words, take this, take that, and give me, what's the value that we have here? Well, just to make sure we're on the same page here. So this one is 30 square meters and this one is 45 square meters. So therefore we have, this is 30 square meters, this is 45 square meters. And what's the total force that is acting on that wall? Or half that wall, because the other half is on the other side. Does anybody have a value here?
So what was the other tributary width? 30 and?
Well, this one here, we have a surface area of 3 meters by 10 meters for the end or the edge of the building. End, I like to call it the end, but some people like to call it the edge. This is 30 square meters here, and this is 3 times 15. This is 45 here.
Okay.
Okay. So that should give you the, so therefore we can end up getting the, so you can tell me what the W is here. The specified wind W is equal to, and of course this is going to give it to you in kilonewtons.
I got 42.12 kilonewtons.
42.4?
0.12.
0.12? Okay.
Yeah.
That's what you got? I'll wait for somebody to concur with you.
Yeah.
Yeah, you got this.
Great. So we got at least 3 people to concur. Now, of course, my WF factored. This is my load factor for wind. If you remember case number 4, where the wind is the principal load. So you got to take the 42.12 and you have to multiply it by 1.4. And that's going to give you your factored load. In other words, your PF here, or your P, actually, well, if you want to call it a P, your wind factored load is so. Does anybody have an answer? What's 42.12 times 1.4?
58.97.
68.
58.
Oh, 58. 58.97.
97.
Wow, kilonewtons. 58.97. Okay, so that's going to be the force that's going to get transmitted, or that the vertical brace has to resist. 58.97. Okay. Now you could have done 2 things. You could have just taken this one here, and then in ADA you could have applied this factor. Okay. Or you can take this and do the analysis manually. I'm going to give you the choice. Okay, so take this one here, put this one in ADA. In ADA, it's always good to put the specified load, and then under your load combination, put a load factor of 1.4. If you're going to be doing it manually, of course, you should be taking this force here to do it manually. I don't know if you guys know how to do that manually, but it's not very complicated. So basically, if you're going to use ADA, this is what you're going to be doing. Okay, in other words, this is the distance between the 2 supports here is 10 meters. Okay, and of course this is exactly halfway. So in other words, this here is at 5 meters. Okay, you basically put a pin support there and a pin support there. It's a pin structure. Okay, you factor the forces here. In other words, you can use a specified force and multiply by your load factor in ADA. So this is the model for your ADA. Okay. And I do suggest that for a sample, start with a HSS of 114 by 114, because these are going to be HSSs, okay? Use this for your HSSs, okay? Run the analysis. Now what's going to happen is that you're going to have tension on one side, you're going to have compression on the other side, okay? So you look at your compression force, and then you look at the length of your member here. Since this is in compression, you look at the length of the member here, and you go get a square HSS whereby the CR value is greater than or equal to the CF value that you got from your ADA. And that's how you design your brace. And keep in mind that and then on this side, the TF value that you have here should be equal to the CR value that you have on that side. So that's how you model it in ADA. Or if you guys know how to do this, you take your factor load here of whatever it was, okay, and you resolve the forces, and I can tell you're going to get exactly the same answer. It's up to you, whichever way you want to do it. In other words, you just resolve these forces, and you can get the force in here, and you can get the force in here. You understand? It's up to you how you want to do the analysis. So model this in ADA. And then, like I said, once you have this compression force here, you go into your, you go into the tables where you have your HSSs, and ADA is going to give you the length of this member here. Take that length from ADA, go into the table and find a CR value that's greater than CF, and that's going to be the size of your brace. And then, of course, it's going to be ample for the tension side, because the tension side is going to be way stronger than it has to be. So because of the compression, you design it as a compression member, and on the tensile strength, it's going to be more than ample. And that's going to be that's it for the brace. And I think that's it. Yeah. So does anybody have any questions before I stop the recording?
Yeah, could you go back one more slide? Sorry.
Sure. How far back do you want me to go? Here?
Yeah, exactly.
Okay, like remember here what I said is that if you're going to be doing ADA, don't use this right away. Put the specified load in ADA, right? And then after that, in your load combination, multiply by 1.4.
Sorry, I don't get it. Yeah, we shouldn't. We should go on ADA and get the specified wind load from ADA, or
No,
That's an option.
you have to tell me what the force is in this member that has to be designed for. You're gonna have to do the analysis. Do it manually. I can do this manually. Understand? I don't have to go to ADA. It's up to you. You either do it on ADA, because I'm pretty sure you guys probably don't remember how to take this and resolve it into components and be able to calculate what the force in each one of these members is. Understand? So I'm asking, you can do the analysis manually, or you can do it with ADA, whichever way you want to do it.
So when you say manually, like, because on ADA, honestly, I can't imagine how, like, I can picture how to start actually the ADA.
Well, there you
on
go.
this-
It's right there.
on
The
this
model's right there. You
analysis.
do 2 pin, you do a support here, you create 3 nodes. In other words, you create a node here, you create a node there, and you create a node there. And then you change this into a support node, leave that as a normal node. And the coordinate here is 0, 0. The coordinate here is 5, 6, and the coordinate here is 10, 0. I mean, come on, it's the easiest thing to model in ADA. And then after that, you make sure you add a member there, make sure you release it on one side. And then you assign this as a preliminary size, because you need to have this in ADA. Then you apply your force, you run your analysis, and you see what the actual force is in your member.
Yeah, just making sure because yeah. Okay, thank
You
you.
know what I mean?
Yeah, I got it.
Okay, so I mean, like, it's not like I'm showing you the model right in front of you. All you got to do is put down the coordinates, put down the, do the modeling, and then run the analysis and get your forces. And then once you have your force, once you have the CF force in here, because here, if you put the force in this direction, the CF force is going to be in here. If you put it in that direction, it's going to be the same thing. The CF force is going to be in there. It doesn't matter which way, where you put it. And then in the other member, you're going to have a TF force, and you're going to see numerically that they're going to be exactly the same values. One's going to be negative, the other one's going to be positive. So in other words, one member is in tension, the other one's in compression.
Okay, good. Because it
Okay.
wasn't clear at first. Thank you.
And that's it. So that's all you need to do for ADA.
Sir, that's a pin, correct? You said.
We're here.
Yeah.
Yeah, you just release it. In other words, because if you
Yeah,
add this
okay.
member here like this, and you add that member there like that, ADA is going to make this fix together. They're going to weld them together. You understand? And
Yeah.
that's not what you have. What you have is that they won't be able to, the moment that develops on this side, won't be able to transfer to that side. So you need to release one side to create a pin connection. Yeah, exactly.
Okay.
And that's why I put that circle there, because that's how ADA shows you that you've pinned this to that. You understand? And you know, some people, they pin, which is redundant, okay? Which is like totally redundant doing that. You only have to pin one side. You know? As a matter of fact, ADA is such a good program. For example, when you're analyzing a truss, okay, when you're analyzing a truss, and a truss is always analyzed. If ever you do this, and next time you guys are going to notice this, if a truss is always analyzed, everything is pin connected on the bridge truss, okay? And if ever, like when after you model an ADA and you select everything, and you actually release all the joints in ADA, okay? If you put pin on all the joints, you're going to actually see ADA, for example, is going to release here, going to release here, and release there. It only releases 3 of the 4 members. The other one becomes redundant. That's why I never understood why people pin everything. It's supposed to be, and even ADA does it correctly. The program does it correctly. You understand? So here, if something is pinned, you only have to release one side. I don't know why you guys release both sides. That is wrong. Not wrong, but redundant. And some programs will give you an error message when you create that kind of redundancy. Okay. Thank God ADA overrides that redundancy. Okay. So there you go. That's it. And I think that's it. So you have all the information, and yeah, that's it. Now, end and show. Okay, so let me just stop sharing. I'm going to put this on pause.